So welcome to the first Phys50 virtual session. As I have said before, in case no one else joined, these sessions will mainly just be me and Freya, or not mainly, only be me and Freya speaking. And then you guys will be able to communicate with us through the chat room. You'll also, Freya, you want to share your screen? You can use like a whiteboard just to show them what we're able to do to communicate. Yeah, we now have whiteboard that Freya and I are able to draw on. So below, I need a mouse trackpad, just like a slow. Yeah, so do we have any questions so far? How do I can't see the chat room wall.
I can.
Oh, there we go. I found it.
Yeah. So if anybody has any questions, just include them in the chat and we can answer them.
Okay. So it looks like most people who are going to be here are here. So I will go ahead and post the link to the attendance sheet. Let me make sure. We got how many people? Oh, we have a lot of people. Dang. Okay. Maybe I'll share.
So we have a question in the chat about important topics for the midterm. Do you want to take that one?
Sure. Hold on. Let me just post. That link will link you to a Google Doc. It is a spreadsheet in which you can just write in your name and your ID under Monday 9/17. Let's just make sure you're not typing it in the same spot as someone else. So let's just try and do this neat and orderly. But to answer your question, while you guys are all doing that, so first of all, I will answer the midterm question. The most important topics, I would probably say mostly just Newton's laws and projectile motion. But to be fair, the way it works with physics is almost everything is interconnected. So there might be problems that require you to utilize various concepts that we've learned, which is actually good because that's what we'll be practicing today. We have two examples that combine various concepts that we have learned. So yeah, so if you just really focus on Newton's laws and understanding the kinematic equations as well, that would be best. And the other question is, will this be posted later? Yes, we will. Once we edit the video, we will post a link to a YouTube video, which you guys can access this at any time. All right, so.
Okay, so.
We'll just go ahead and get started, then people can continue to fill out the attendance sheet as we go. It says you need to request permission. If you are using your, if you are using your SJSU email to try to access the sheet, it shouldn't need permission. It's available to all SJSU students. So you can sign out of your Google account, sign into your San Jose State one, and give it a try, and you should be able to access the attendance sheet. So the way this will work is Freya will be leading most of the example. I will be fielding your guys' questions. All of the important ones, such as the midterm one, I will input onto the PowerPoint at the end of the session. And I will be, also contributing if, to help you guys understand like the kind of thought process you guys need to have when approaching these problems. But Freya, you want to go ahead and get started with example one?
Yep. So let's just take a look at the problem first. I'll share my screen so you can see that. Okay. So example number one. This is going to kind of touch on rotational problems and projectile motion, which are both topics you should be looking at for the midterm. So for this problem, a ball is attached to a rope that is swinging in a circle of radius 3 meters. At point P, the rope snaps and the ball is launched at a certain initial velocity and angle. It then travels as a projectile for a certain horizontal distance. What is that horizontal distance? So first it's going to be moving in a circle, then next it will be traveling as a projectile. So there's kind of two different parts to this problem. So looking at the given information and what we're solving for, Josh, what do you think the first step that we would take here is?
Well, it looks like we're given the radius of the circle, right? And if we're initially moving in circular motion and we want to convert to projectile motion, we're going to want to know the initial speed and the angle that it is launched at. It says that we're given the angle. So we pretty much just need the initial speed. So the way we could do that is by calculating the speed using one of the equations for circular motion, which would be acceleration centripetal is equal to v squared over r. And we are given r and the centripetal acceleration, so it shouldn't be too hard.
Okay, so the equation that we'd be using would be centripetal acceleration, AC, is equal to v squared over r. This would allow us to calculate our initial velocity. Just a reminder, everybody should have their mics muted and their videos off in this chat. Okay, so we're given that the initial acceleration is, that the acceleration is 6.2 meters per second squared. And the radius is 3 meters, but we don't know what the velocity is. So you can set up the problem this way. And then if you calculate the velocity using your calculator, you end up with a value of 4.313.
And that is done by multiplying both sides by 3 and then taking the square root of that value.
Exactly. So this would be your velocity at the time when the rope snaps and the projectile is projected. So you know what the initial velocity is in this problem. And you're given that the angle is 27 degrees and that it's a height of 5.2 meters. So if you're drawing that out, it would look something like this. So 5.2 meters.
We don't have any questions about how we've gotten to this part.
So
Does not look like it. If you do, you can post them at any time, and I will mark them down.
okay, if there are no questions.
So I imagine the next step, now that we have, or just purely, we can forget entirely about the first part of the problem because we are now in projectile motion. We're not in circular motion. So that's a good strategy to use when taking a test. Is you want to separate the problem into parts to better be able to handle it. So now that we're in the projectile motion part, we should start off by making our charts of the things that we know.
Okay, so do you want to write out the chart, Josh?
Sure. So we have x, t, dx, And I could write the acceleration in the x direction. However, in projectile motion, the acceleration in the x direction is always 0. So we can just leave that out. However, we also have our y position. We have the left of the y. A lot of background noise on someone's mic. Freya, would you be able to try and figure that out? So our acceleration in the y direction due to gravity is negative 9.8. Right? That's meters per second squared.
Okay.
We have our initial x position is 0. Our initial y position is the 5.2 that is over on our drawing. And we'll just assume that time equals 0 initially. And then both vx and vy we'll able to calculate using the components of our velocity vector. You wanna do that part, Freya?
Yes. So, one second. Just mute all. Okay. So, still hear me? So we have our values that we know, and can make that a little smaller so we can see it. Okay. So
question. They asked why is t equal to 0 for both x and y. It is because time doesn't change depending on whichever direction you're going. Time is, after 2 seconds, it's not 1 second one way and 2 seconds another. It's 2 seconds for both.
exactly.
So you don't even necessarily need to include t in both of these because they will just always end up being the same. But I like to do it just for it to make a little bit more sense. Whoa.
Sorry, gotta get the hang of this.
That's interesting.
This is what I get for using the whiteboard. Okay.
We go a little better, maybe. Where's the y? Could just undo. Just keeping it moving though, we now have to resort to kinematic equations in order to find, because what the problem is asking for is the horizontal distance. And so we only need one more value in the y chart, which is velocity in the y direction initially. So why don't we work, we use one of the kinematic equations in the y direction first. Which one do you think we should use, Freya?
Okay, so the kinematic equations that are really useful in general for projectile motion problems are v squared equals v initial squared plus 2a delta x. V equals v initial plus at, and delta x equals v initial t plus 1/2 at squared. So those are the three equations that are going to be applied in a lot of projectile motion problems, and they're a really good thing to remember. So for this problem, what we want to know is we want to know how much time it spends in the air. And to do that, we need to figure out, so we know what its initial velocity is. We know what acceleration is because in a projectile motion problem, acceleration will be gravity. And we know how far it travels in the y distance. So given those three, we can figure out how much time it spends in the air. So given that that's what we're solving for, which equation do you think we would use, Josh?
I think it would probably be best to solve for time. So we probably don't need the top one, considering that one doesn't have time. Because we want to find the time that it lands. So we have most of our values for the y, so we probably want to use one that has initial y velocity, acceleration, time, and position. And the only one that has that would be the bottom equation.
Okay, yes. So given the variables that you know and the ones you're solving for, the third equation is one that makes the most sense to use. So we know that the change in distance would be negative 5.2 meters. We know that the initial velocity is going to be 4.313 meters per second.
The reason the displacement in the y direction is negative is because the ball is moving down. And to answer the question someone just asked, if you have a positive y, shouldn't you have a positive acceleration as well? No, because if there was a positive acceleration, the ball would shoot out upwards into space, and we'd never know where it went. Gravity is always negative, pointing down towards the center of the Earth.
There's a T there as well. So this would be our equation. So we have, we're using the equation which is y equals y initial plus v initial t plus 1/2 at squared. So given that our change in distance is going to be negative 5.2 meters, our initial velocity is the y component, which is 4.313 sine of 27 degrees times t, plus 1/2 times our acceleration, which is gravity in projectile motion problems, which is negative 9.8 meters per second squared, times t squared.
This gives us a quadratic equation in which we will have to use the quadratic formula, which I know isn't very friendly, but it's something you'll have to get used to. And so why don't we go ahead and rewrite our equation out here, and then we can write it as we can use the quadratic formula to find the time that it takes for it to land.
Okay, so that's the formula that we just had. And we can rewrite it in a way that looks a little closer to the form of ax squared plus bx plus c that you often see in the quadratic formula. And to do that, we would write negative 4.9 t squared plus 1.958 t plus 5.2 meters equals 0. So this is just if you plug it into your calculator and rewrite it so that you have a, b, and c, which will allow you to plug it into the quadratic formula, which is negative b plus or minus square root of b squared minus 4ac all over 2a. So that's basically the quadratic formula, which I'm sure most of you have used before. And we're just going to plug in our values. So if you plug your numbers into this formula, you get two possible values of t. T equals 1.2646 seconds or negative 0.857 seconds.
So the way that we run into that issue is because of, as someone mentioned, the plus or minus causes difficulty. However, because our acceleration is negative, that means the bottom is going to be negative. And since we want our time to be top, that means the top and the bottom have to be negative. So if we added the square root of b squared minus 4ac to the negative b, that would give us a positive number. And a positive divided by a negative would be negative, giving us our negative time here. But you can't have negative time. So you have to use the subtraction sign, which would then leave a negative answer on top and a negative answer on bottom, giving us our final positive p.
Yes, so as we know we can't have negative time, that means that we're able to conclude that 1.2646 seconds is how long it's spent in the air, which then allows us to calculate our horizontal distance. So which equation do you think we would use for that, Josh?
Well, one of the equations uses only the, well, actually we could use the same one we used earlier, because the acceleration in the x direction would be 0, and then the velocity in the x direction is constant. So we end up just having our change in x is equal to the velocity in the x direction times time, because the acceleration is 0. And
exactly.
Now know time, and we just need to find the horizontal component, which was 4 point something cosine of 27 degrees. Then we
Right.
just multiply, and that should be our displacement.
So we know that the acceleration is going to be 0 because it's horizontal motion, and there is no acceleration in projectile motion problems in the horizontal direction. So that just leaves us with v initial times t. Now, we know that v initial was 4.313 meters per second, and because it's the x component, that would be cosine of 27 degrees. And we just calculated the time, which is 1.2646 seconds. So given this, if we plug it into the calculator, that gives us a horizontal distance of 4.86 meters, and that will be our final answer.
So someone asked a good question. They asked, so will there always be a positive p-value and a negative p-value for every single case? Well, that's the thing, is that because the bottom is negative due to the acceleration, we're always going to need one of the answers to be negative. So I mean, so one of them, either one of them is negative or both of them is negative, and if both of them are negative, one of them will give you such an odd value that you can rule it out. Like, oh, it takes 0.05 seconds for this thing to fly through the air. That's obviously not going to be the answer, because nothing flies that quickly. So like either one answer will be negative time, and so you can just cancel that out, or it will be such an outlandish value that you can just rule it out as well.
Okay, are there any other questions on this problem, how we got to the final answer?
Does not look like it. I will address them if they pop up. So we'll go ahead, it is 12:30, we'll move on to the next example.
Okay, so, screen again. Okay, so for example number 2, this one is also going to involve projectile motion, but in this case, we're also looking at forces. So a box starts from rest at the bottom of a ramp. It's a 3 kilogram box moving up a ramp that's 5 meters tall, and it's being pulled by a force of 45 newtons. It reaches the top of the ramp after 2 seconds, and at that point it will become a projectile that is traveling a certain distance horizontally. So how far does it travel in the x direction?
So similarly to the last problem, we end with the projectile motion problem, but to get there, we have to pull on our knowledge from other kinds of motion. In this instance, we have forces, right? So forces, according to Newton's second law, is the sum of the forces will equal to the mass times acceleration. And so if we're able to find the acceleration, we are given the time it takes, we can find our final velocity as it goes off the ramp, which then, since we're splitting the problem into 2 parts, will be the initial velocity for the projectile.
Okay, so we'll start drawing this out. See how that works. Sure. Okay, so a good way to start any of these problems where there's some kind of object moving is to draw it out first. So you have your ramp, which is 5 meters tall, a box of 3 kilograms moving upwards with a 45 Newton force. And the time equals 2 seconds at the top of the ramp and 0 seconds at the bottom.
Hey, Freya, I have an idea. When we're doing the showing the work for the math, maybe you could leave out the units. That way it's less cluttered because we can understand it better.
Yeah.
And if they're confused about the units, then you guys can just ask this question.
Yeah, I'll leave out the units on the equations then. You're right, that might make it a little easier. Yes,
Oh, yep.
there is an angle. It's
Good
a
catch.
30-degree angle. Yeah, that's a good detail, otherwise make it a little bit more difficult to solve. So given that
I have a question for the class. Do we want initial velocity, when we want to find the initial velocity, do we want that in the x direction, the y direction, or do we want that to be along the ramp? You guys can put it in the chat box, or if you, I'll give you guys like 5 seconds if no one's confident enough. Yes, someone said along the ramp, that is correct. Yeah. Because if we find the final velocity of this box going up the ramp, right as it goes off the ramp, that becomes our initial velocity, and we will have the magnitude, which we'll calculate, and at 30 degrees. So that will be the velocity that we're given for the projectile motion problem.
Okay, so yes, our initial velocity in this first part of the problem we're looking at is our initial velocity on the ramp. And we want to figure out what is our final velocity at that top point, because that's when it starts to become a projectile. So again, our equations that we're going to be using are V equals V initial plus AT.
Don't we need to use the force, Newton's laws first?
Yeah, I'm just going to write out all of the equations just so you can see. It's important to just remember which equations you have at your disposal so that when you're trying to figure out the next step, you can think about what you have and what you need to calculate.
Makes sense. I was just mainly asking to preserve room on the whiteboard because it's not that large.
And then the equation that Josh was mentioning, Newton's law, force equals mass times acceleration. So that's something that's going to come up most of the time when you have a problem like this, where there's a force pulling the object upwards, or any kind of force acting upon the object. So the first step here is that we would want to figure out what the acceleration is. We know what...
I'll go for it.
Huh?
Go for it.
Okay. So we know what the forces are that are acting on the box. We have gravity, which points directly downwards, which is equal to mass times gravity. That's the weight of the object. We have the normal force, which is perpendicular to the surface of the ramp. And we have the pulling force, which we can just call F. So
if we want to find the acceleration, as someone said earlier, along the ramp, do we need the normal force? Is there any component of the normal force that is going along the ramp?
So the normal force will actually not be necessary in this, because as you can see from this, the gravity vector or the weight vector has components in along the ramp and perpendicular to it. And the perpendicular component cancels out with the normal force because they're equal. So we won't actually have to worry about that. What we're going to be looking at is this, the X component, the component that's parallel to the ramp, because that's what's going to account for the force that's acting on the object in the direction of the acceleration. So the force total along the ramp is going to be equal to the pulling force, so the 45 newtons, minus mg sine 30 degrees.
This angle right here of the weight is equivalent to the incline of the ramp.
Yes, so that's the angle is right there. So somebody asked, why is it a minus? Because they're acting in opposite directions. So this vector for the X component of gravity is pointing down the ramp, whereas the force vector is pulling up the ramp. So if you drew your coordinate plane, it would be positive, positive, negative, negative. Yes, because the acceleration is negative, so its X component would also be negative. So if we plug in values, so we can get an actual number here, we get the force total, the sum of all the forces, is equal to 45 newtons minus the 3 kilograms times 9.81 meters per second times sine of 30 degrees.
And that, when we plug that into a calculator to save time, that should give us
30.3 newtons.
Yeah, 30.3 newtons.
Yes, so that's the sum of all of our forces. And as we know, the sum of all of our forces is equal to mass times acceleration. So 30.3 newtons is equal to 3 kilograms times acceleration, which gives us an acceleration vector, an acceleration value of 10.1 meters per second squared.
Now this is the acceleration in the direction of the ramp. And that is because the forces that we summed up are only the forces acting in the direction of the ramp. So if we summed all the forces, including if we changed our coordinate system, that might be different, but we are specifying our coordinate system along the ramp because that's the acceleration that we want to find. So now that we have our acceleration in that direction, what we can do is we can multiply our acceleration by the time it takes to go across the ramp. Because if you multiply acceleration by time, then you get velocity. You can kind of see that in the equation up here.
We have a question about why we couldn't just plug the 45 newtons into the force equals mass times acceleration equation. So in that equation, it's the sum of all the forces acting upon the block in the direction that you're looking at. And in this case, the pulling force, the 45 newtons, wasn't the only thing acting on the block. It was also being pulled in the other direction by the force of gravity. So that has to be included in your sum of all your forces. Okay, so given that we have acceleration and that we know how long it takes to move up the ramp, we can then plug this value in to the V equals V initial plus AT equation. We know that V initial is 0, so we can just disregard that. And that means that the velocity at the top of the ramp is equal to the acceleration of 10.1 times the time of 2 seconds, which we were given in the problem, which means that our final velocity is 20.2 meters per second.
And this velocity is at an angle of 30 degrees because that is the angle of the ramp.
Okay.
So we have now figured out all that we need from the forces part of this problem. We now have our, for our projectile motion, we have our initial velocity, both the magnitude and the direction. So we can forget everything that we just did and just remember this last part. I mean, don't forget everything, of course, because, you know, you want to learn, but you don't need it for the rest of the problem.
So starting from the top of the ramp, kind of ignoring the first part, we can treat it as a projectile motion problem. So we have an object projected at a 30-degree angle, velocity of 20.2 meters per second, and a height of 5 meters. And then what we're trying to figure out is how far it goes in the x direction. So this is very similar to the last problem.
So just like the last problem, we can kind of just take a shortcut here, just to preserve time. Last time we drew out all the charts, right? And then we used those to figure out what we should find. But since in this problem we're given exactly the same thing as we were the last time, we know the initial velocity and the angle, as well as the initial position, both in the y and x direction, and we're trying to find the horizontal x direction. We will take the exact same approach and use, this equation that Freya just wrote out for us.
Okay, so this is the same step we took last time. We're just skipping a couple steps here to make it a little faster. But so given this, if you plug in your values, you have negative 5 meters equals 20.2 sine of 30 degrees plus 1/2 times negative 9.8 times t squared. And yes, there's a t value here. So again, set it up for the quadratic formula. If you rewrite it to look a little bit more like that, you get negative 4.9 t squared plus 10.1 t.
10.1 because the sine of 30 is 1/2, and so you just divide that by 2.
Yes, a equals 0. If you plug that into your quadratic formula again, you get 2 possible values of t, which are negative 0.42 seconds and 2.525 seconds. So like the last problem again, we can eliminate this negative value and choose the positive one, as we know that time cannot be negative. So we know that it spends 2.525 seconds in the air. And then what would we do for the last step, Josh?
Well, just like the last problem, we then plug this time, because time is constant regarding of direction, we plug this into the position and time kinematic equation in the x direction.
Great. So we know that there's no acceleration in the x direction. There is an initial velocity of 20.2 cosine 30 degrees. And we know that the time, which we just calculated, was 2.525 seconds, which gives us a delta x value of 44.18 meters, which is our final answer.
And remember, guys, something that you will run into in physics a lot is rounding errors. Because we have so many equations, so many things like all of the squares and the square roots that we've done, you will, like, for example, if you got like, I don't know, 43.8 or something like that, you probably wouldn't even get marked down on the exam because it just comes down to rounding error. If you show your work, do all the steps right, and you're off by like a couple decimals, I doubt that he would mark you down for that, because you know physics is about the concepts, not about getting the right numerical answer.
Okay. So are there any questions on how we reached the final answer here, or the equations we're using, anything like that?
Does not look like it.
Okay. Then
We're done with example 2. The last thing on our agenda was we wanted to have the last 10 minutes be open to you guys to answer any questions about the class, about the midterm, about anything, you know, just free flowing, shooting any questions you have at us, and we would do our best to answer them. So go ahead, and if you have any, you can post them. Oh, all right, we got one. This recording video will be posted online to go back and review. Yes, that is correct. Once we're done with the session, we will take the recording, we'll edit the video, and we will post it on YouTube, and then we will put the link to YouTube on campus.
Yep.
Okay, so let's go in order. Could you go over the 4 kinematic equations and explain what each is useful for solving equations?
Okay, so I can write down these equations and we can just discuss how you would choose which one to use. Okay, so the kinematic equations that are going to come up a lot are V squared equals V initial squared plus 2a, and then you could do x minus x initial. Okay, so those are the equations that you're going to use a lot when you're doing projectile motion problems. Now, they're not specific for solving any kind of problem. Like you can't say, I'm only going to use this on these kinds of problems, but it's more about looking at which variables you have. So say that you've got initial velocity and final velocity and time, and you're solving for acceleration, then you might use the second problem here. It kind of just depends on what variable you're solving for and what information you're given. That's how you would choose your equations. You would just kind of assess the situation based on the problem.
There's also a couple tricks that you can do with this. Oh, I lost my marker. Oh, there it is. For example, if the problem has nothing to do with time, right? Like if you're not given time, or if you don't want to find time, then you probably want to use this one, right? Because the only one that doesn't use time. And if you try to use either of the other ones, then it wouldn't work out very well because you don't have time. And if you do want to find time, then yeah, you would use one of these two depending on what the other things you're given. In the same way, if you aren't given any position, right, then you would use, let me change the color here, this one, because this one doesn't do a position while both of the other ones do. So it's really up to you guys to analyze what you're given and what you need, and then make the right choice. Technically, you can use any combination of the equations. It really just comes down to which one is fastest and which one is the easiest math and introduces the least rounding errors. It's just a skill that you'll develop as you practice.
Yeah. Another aspect of that is if you don't have final velocity, which might be the case in a lot of projectile motion problems,
right,
then you would use this third one. It's just kind of eliminating equations based on what you don't have and then choosing the one that'll get you to your answer the fastest and the easiest. Okay, are there any other questions?
How about questions regarding relative motion or circular motion? Those ones are probably not as likely to be covered as heavily on the exam, but they are still free reign to have questions on. I imagine those will probably be more in the multiple choice section rather than the long problem solving question. But does anyone have any questions about those concepts? So you guys are masters of relative motion and circular motion then. All right, good to know. I'll come to you guys if I need help with my homework. It's a test curve. I mean, we are not responsible for any grading. Literally the only influence we have on any of your grades is the extra credit you get for attending our sessions. So, I mean, my experience is that most professors curve at least slightly. So I don't know for sure. That would be a question we'd have to ask him in class. But I'm pretty sure he's not even going to be there tomorrow. We have Crest tomorrow. But yeah.
The next virtual session will be in 2 weeks, I believe. I think we'll be doing these bi-monthly. Is that right, Josh?
Yes, we will. Our plan so far is to do them bi-monthly. These sessions, as you guys probably could guess, take a lot more preparation and planning, and there's a lot more difficulties. So it can make it difficult to do as many virtual sessions as you do in person. However, as we get the swing of things, or if the demand increases, we might increase number of sessions. This is a brand new program actually. Like, I think one class offered virtual sessions last semester, and that was only like 2. But like, this is a brand new program this semester, so we're rolling out the program, kind of seeing how it goes.
Yeah, and the other question is about SI sessions just in general. So we have 2 more until the test, I believe. Josh has one on Wednesday. I also have one on Wednesday. So one at 12 and one at 3.
Well, the test is next Tuesday, right?
Next Tuesday. Okay, so yeah, we'll actually have 4 more until the session then, because I have office hours on Thursday. Josh has a session on Friday. So there are 4 sessions until the test.
And yes, as far as time of the day goes, for the in-person sessions, those are constant throughout the semester, unless we tell you otherwise. It will always be the same day, the same time. And yes, all of this is on announcement. Or if you find something, if you have a question that you don't see is answered in the announcement, then just message one of us and we can make sure everyone knows that. Is there a way to check how many SI sessions you have been to. I have my own list of everyone who's attended my sessions, and we also now have the attendance for this one. And
Yeah,
Freya,
I have my list. We
So-
both have a list of who's been attending the sessions, so you can check with us. Also, it's just a good idea to keep track of it yourself as well, just so that you make sure you attend the 3 sessions for the extra credit, which is good.
Yeah. Can we cover specific homework problems? That is what these times are for. I'd like to incorporate 10 minutes. I mean, unfortunately, I sometimes go over that and end up, only having like 5 minutes at the end. But I like to leave the last 10 minutes to answer specific problems, be it from your homework or from just problems you ran into on the textbook. We don't have time to do that now because we're closing out here in a couple minutes. But in the in-person sessions, yes, we will be able to do that. The virtual ones, not as much because, there's a lot more people and there's a communication barrier. It's just a lot more difficult. So
yeah, I also have office hours, so that is more for specific homework problems, because for those there isn't a lesson plan or any examples that we have set up. So if you come to the office hours and you have homework questions, I can go over that.
Any other questions? Yes, that is a good point. I am actually personally surprised by how many announcements Professor Garcia makes, but that's just his style, I guess. So I think we will try and get more in the habit of continuing to post all the times together. That way it's more readily apparent to you guys what times the sessions are at.
Yeah, we can make one announcement with everything listed to make it a little clearer.
Yeah. And we'll also include the virtual times on that now. So I believe that the virtual sessions will usually be the same time as well. Virtual sessions, because we don't need a room for them, are not as locked in. So if we need to, or if something comes up, we can move it from this time. But for the most part, it's planned for Mondays at 12.
Yeah.
Yeah, no problem, guys. It's a pleasure.
Yeah, and thank you guys for watching this. It's yeah, we're gonna be working on it a little bit.
Donate money. No, we get paid to do it, so I mean, it's not like we're slaving away.
Yeah.
Someone asked, the Thursday office hours do count towards SI. Right?
Yeah.
Office hours in peer connections do count towards SI. However, office hours with Professor Garcia, those are separate. So long as what you're doing is related to peer connections, for the most part, that counts towards your SI attendance count.
Yeah, so virtual SI, regular SI, and my office hours all count towards that, the number of times you attend.
And if you guys ever need any extra help, there's plenty of physics tutors that Peer Connections offers. They are more one-on-one and can help you with individual concepts and stuff like that. But yeah.
Yeah.
All right, guys. Well, thank you for attending. It has been a quality first session. And I think we will end it here.
Yep, so this will be the end of the session. Everything will be posted online. And yeah, we'll see you guys in class.